All right, so last time we saw a network just absolutely melt down because of one extra cable. So what do? We need those backup paths, right? But how do we build them without, setting the whole thing on fire? Well, let's get into it because the solution is actually pretty brilliant. So, just to jog your memory, the first big problem was the broadcast storm. Remember that? A single broadcast frame gets into a loop and just never stops. It just keeps circling, copying itself, getting louder and louder until it's a full-blown hurricane of data that chokes out everything. Total network shutdown. And if that wasn't bad enough, it gets even crazier. While all this is happening, the switches start getting, well, completely confused. They see a device coming from one port, then another, then back again. Their MAC address tables, their whole map of the network, start flipping out. It's like the network completely loses its memory, and poof, nobody can talk to anybody. So that's the big puzzle, right? We have to have backup links. If a cable gets caught, you need the network to stay up. But we just saw that those very same backup links can cause a total meltdown. How in the world do you have one without the other? Well, the answer, and it's a classic, is the spanning tree protocol. You'll hear it called STP. This thing was invented for this one specific reason, to let us have all the backup cables we want without the catastrophic loops. It's how we get our redundancy without the risk. Basically, STP's whole mission in life is to look at all the connections you've made and say, okay, great, we have options. Then it intelligently picks the best path and puts all the other ones on standby. It doesn't get rid of them, it just logically turns them off for a bit, stopping a loop before it even has a chance to start. And this is such a key concept to get. Physically, you can walk into the server room and see the cables making a circle. The loop is there. But STP creates this logical view, like an invisible layer on top of the physical network. And in that view, one of those cables is just paused. It's on hold. So logically, in the world where data travels, there is no loop. That's exactly why it's called spanning tree. It spans the whole network, connecting everything, but it does it by building a tree structure. And think about a real tree, right? You've got a trunk, branches, smaller branches, but you never see a branch loop back and connect to itself. No loops. That's the whole idea. Okay, so how does this magic actually happen? It sounds complicated, right? A bunch of separate switches all working together to build this perfect loop-free map automatically. But it really boils down to a pretty clever three-step process. It's simple, really. Step 1, they elect a boss, called the root bridge. Step 2, everyone else figures out the fastest way to get to that boss. And step 3, any other extra path gets shut down. That's it. Elect, find the best path, block the rest. Now let's look at each of those pieces. So, step 1, the election. This is all about picking a single point of reference. The root bridge becomes the "you are here" star on the map for the entire network. Every single path calculation, every decision every other switch makes is all based on how do I get to the root bridge? So how do they vote? They use something called a bridge ID. Think of it like a campaign sign. It's got two parts. First, a priority number, and this is one we can actually change as network admins. And second, the switch's own MAC address, which is totally unique. You combine those two, and every switch has its own unique ID to enter into the election. And the winner is, well, it's not very dramatic. The switch with the lowest bridge ID number wins. That's it. It's a lowest number wins contest. And the best part? This happens all by itself the moment you plug everything in. The switches just start talking and figure it out in seconds. Okay, so we have a leader. The root bridge is chosen. Now, every other switch has to turn on its internal GPS. Its job is to calculate the absolute best, fastest, most direct route to get to that root bridge. The physical port on the switch that connects to that best path, that's called the root port, and every non-root switch gets exactly one. But what does best even mean here? It's not about distance, it's about cost. And in the world of STP, cost just means speed. It's kind of backwards. A really fast link, like a 10 gig connection, has a low cost. A slower 1 gig link has a higher cost. So STP is always looking for the path with the lowest total cost. It's a speed freak. And that brings us to the final piece of the puzzle. What happens to all the other ports, the ones that aren't the single best path to the root? Well, any port that could create a loop gets put into a blocking state. It's essentially put on mute. It won't forward any data, it won't learn any MAC addresses, it just sits there listening, waiting. It's our backup, ready to spring into action the second that primary path goes down. So let's zoom out. You have this whole process, electing a route, finding the best paths, and blocking the rest. And what you end up with is the holy grail of network design. You get to have all your physical backup cables plugged in and ready, but the network operates in a perfectly safe, stable, loop-free state.
When the dust settles, every port on the network has a very specific role. You've got your route ports, which are always pointing towards the leader. You've got designated ports, which are in charge of forwarding traffic away from the leader on a certain cable. And then you have the blocked ports, sitting on the bench, ready to jump in. Every connection has a clear job.
I mean, the difference here is just huge. Think about it. Before STP, you plug in one extra cable for safety, and you take down the entire company. After STP, you plug in that exact same cable, and you've just created a smart, self-healing network that can survive a failure without anyone even noticing. It's a total game changer.
So let's just boil it down one last time. What does STP do? 3 things. It elects a boss, finds the fastest paths to the boss, blocks all the other paths. That's it. That simple, automatic logic is running on millions of networks right now, keeping them from falling apart.
You know, maybe the best way to think about STP is like the silent, unsung hero of the network. It's this invisible control system, constantly working in the background, making sure that all the careful planning we do for redundancy doesn't backfire and become our biggest weakness. But this whole automatic process leaves us with a really important question. If the election is just lowest number wins, what if your oldest, slowest switch happens to have the lowest MAC address? You don't want that one to be the center of your universe. So how can we, the network engineers, influence this election? How do we rig the vote to make sure the right switch wins? Well, that's a fantastic question, and we'll dig into that next time.